let's have a look and see what is actually what we were supposed to have done. Let's check off whether we did or not. Did we define work as the product of displacement and the component force parallel to the displacement when the force is constant?
Sure. Probably.
Yeah, we certainly talked about work as the product of displacement and force, right? So we define work to be F times D, and F has to be parallel to the displacement. That means it has to be in the same direction as the displacement, right?
We never talked about displacement, we just talked about...
Well, distance, displacement.
Yeah, so then why are you saying the different things when they're saying?
Well, the distance is just, displacement is just distance plus a direction. If the force is at an angle, then what portion of the force goes towards the work? Just that is in the same direction as the displacement. Right? FH. You should have this list of our stuff already, right? You should have got it at the start of the unit.
We're not using like FH for formulas and stuff for this, are we? We've never done that.
Yeah, we did.
Oh, we did it with this unit.
Yes, Hannah. No, we did. Yes.
No, well, okay,
I can show you if you're going to push me on it.
Great, I will.
Okay. All that means is
Well,
I did, Hannah. Yes. Yes. No, I do not. Okay, all that I'm saying is, if you've got an object, right, we've got work is equal to FD. If the force is applied at some angle, okay, and you've got this horizontal component here, and the object moves sideways, the work is the horizontal component of the force, FH, times the D. Okay, if the force is 100 and the horizontal component is 60, do I put 100 or do I put 60 in for FH? I put 60. That's all that I'm saying.
You did it.
We did that. Yes, we did.
So, 100 for that.
Okay? The component of the force that does the work is that which is parallel to the displacement. No different than if I'm carrying my briefcase across, remember this one? Remember carrying the briefcase like this? Yeah. Which way is the force? Up, but the displacement is this way. Therefore, no work.
yeah.
We did that. I remember walking across the front of the room pretending I was a tall, skinny man with a big briefcase with no hair.
So you have to use like some posts and stuff?
Yeah, well, you guys had to know how to find FH. FH equals F cos theta, right?
Oh, wait, so you would give us like the F?
I'd have to give you the angle there.
And you'd give us the F?
And I'd give you the F, and you have to find the FH. Yeah.
Pause it again?
Yeah. Manny, sorry, I didn't get to you. What were you asking? Yeah, absolutely. No, FH times D. Times. Work is force times distance. Times. Okay, did we determine work from the area under the force position graph for any force, including positive or negative force and a uniformly changing force? We found, more than once I showed you, force distance. What's the area under the graph? F times D. Work is F times D, therefore, work is the area under the graph. And if that graph is above 0, then it's positive work, and if it's below 0, it's negative work, right? If it's a uniformly changing force, in other words, if the force is at an angle like this, well, then it's not a rectangle anymore, it's a triangle, right? Half the base times the height. Did we describe work as a transfer of energy, including positive and negative work, kinetic energy, conservation energy? Yeah, I think I did, right? More than once I said, you do work, it is transformed into potential or transformed into kinetic, right? When you do work, you are transforming energy. Give examples of various forms of energy and describe qualitatively the means by which they can perform work. I don't even really know what that means.
Yeah.
I guess kinetic and potential, right? Various forms of energy. How do they do work? Well, kinetic energy applies a force, I suppose. Potential energy, there's the potential for a force. I'm not really sure what that means. Derive the equation for kinetic energy using kinematics equations? For sure I did that. Am I going to test you on that?
Which one is that?
mv squared over 2 or half mv squared? We did it. Well, I ain't going to test you on it.
Okay.
Did we derive the equation for gravitational potential energy? E equals mgh? Uh-huh. I'm not going to test you on it. Did we experiment to determine Hooke's law? With the springs? We sure did. Am I going to test you on it? No, it doesn't say that I'm not supposed to test you on it. We did an experiment. You had an experience. Did we derive an equation for the potential energy of a spring using Hooke's law? What is Hooke's law, or the potential energy of a spring? US equals?
1/2 something.
1/2 kx squared. We did that.
What's the X stand for now?
Distance. And here's the one that always is the big daddy. Solve problems related to the conservation of energy, including gravitational and spring potential and kinetic energy.
Okay.
So, let's talk types of problems.
So can you go over 14?
Sure. Okay.
Right.
Okay. Well, let me just go through the types of problems first, then we'll have a look, right? So there will be standard sort of W equals FD. Manny, can you hold that sheet up you had it before? I think it said introductory work on it, right? Yeah. So there will be stuff coming off there, right? Could it be work on a flat surface? Yes. Could it be work on a flat surface at an angle? Yes. Could it be an object going up a ramp? Sure. What does that mean? As soon as I say ramps, it means things like that's a D. FD is equal to mg sine theta. It's Fn is equal to mg cos theta. Right?
For the test, we have to know stuff like,
FF over Fn is mu. Go ahead, Jason.
no.
No, ask it. Go ahead, ask.
No, are we gonna have to know like those formulas like your VS?
Oh yeah, you always gotta know those.
But we haven't used any of them for this except
Oh,
like once.
you should have.
Use it a
Yeah,
little bit.
the kinetic energy ones. Yeah.
They use it, you'd rather us not use it. Because I did it.
Oh, okay. For some. That's somewhat two-handed. About the only real set of formulas that you're not going to really use would probably be those circular motions, right? Did we see any circular motion in work?
I did not see any circles.
No, I didn't see any. So that's about the only group of ones that you won't have.
Do we need to know that like velocity?
Yeah, oh yeah, like, yeah, D equals BIT plus half AT squared. Those ones you always got to know. Always. So that's sort of all the work ones. After that, what else is there going to be? Well, for sure, there's going to be kinetic energy, mv squared over 2. There'll probably be a basic kinetic energy one. Velocity must be in meters, by the definition of the kinetic energy is measured in joules. There'll be potential mgh ones, which by themselves are pretty easy. Height must be in meters, right? Mass in kilograms.
What's that one formula called? It's like ET equals EK.
Yeah, I'll get to that right away, yeah. And sort of, that's actually the next one there, Steve, would be sort of what I would call the combination of those two, right? It would be like conservation of energy, where the total in any system, total is EK plus U, right? Kinetic energy plus potential. Now that potential could be either spring or gravitational, right? And then there's all that spring stuff. US equals 1/2 kx squared. So basically, it would be like kinetic energy, potential energy, combination of those two, kinetic energy, spring energy, combination of those two. There's enough in there. Yeah. I'm pausing for questions. I'm not. Are we good? As good as we're going to be?
Yeah.
Okay. 14.
14B. Well, I mean,
Can you give me the? I don't know. You know what sheet you're talking about, man.
You want to read the question later?
Yeah.
Okay. So now we're looking for in part B. It's when the x is how much? 0.4?
Yes.
Or 0.4. Okay. So again, the total energy is going to be made up of kinetic plus potential, spring energy. The total energy at the start and at the end is equal to 125.
Can you go over back to A, like explain how you did x equals, why did you do 2 times 1.5?
Well, I took, this is 5, this is 1/2. Okay, well, let's do it this way then. Yeah, okay. 1/2 of 250? Or 1/2 of 500? 250, right? Okay, so it's going to be 125 is equal to 250 x squared. So it's going to be 125 all over 250, isn't it?
What did you just show? 250 times x squared?
Okay.
Wait, what did I do? What's that?
Okay. Let me write out all the steps.
Oh, wait, no, I did do something like that. I don't know how I did it, but I did it.
Right?
Yeah, right.
So why do you put
Oh, because equal, yeah.
125 as the total energy or whatever when that was just the kinetic?
Because at the start that was the total energy. Before the spring was compressed, there was no spring energy at all. At the start, the kinetic is 125 and the spring energy is 0. The spring's just sitting there doing nothing. It's not compressed, it's not stretched, it has 0 energy. It's like a teenager on a Monday morning.
But if it's like moving, you need to find the energy by finding velocity, which shows it's moving because it should have energy.
What's moving?
Well, when you have to find EK, you have velocity, so it shows that it's moving. It should have energy, so
But
why?
what's moving, Hannah?
I don't know.
This thing's moving, not the spring. The object, the 10 kilogram object is the thing that is moving. The spring is just sitting there. It's not compressed, it's not stretched. The spring has no energy.
Back to B.
She's already on to B.
Oh,
She doesn't like the fact that the ET is 125. The total energy is 125 because the spring has no energy to begin with. All right, so whatever kinetic energy is left is when there is a spring energy of some value that we don't know at 0.4. So that's equal to 1/2 kx squared. So 125 is EK plus 1/2. What's our spring constant here? 500? 500. The x squared is 0.4 squared. So in other words, find out how much spring energy is there at 0.4.
Is it like potential spring energy?
Potential spring energy.
What is the difference between spring energy
Spring energy and what?
and spring energy and spring energy?
Same thing. They are not different.
what is it?
They are not different. Springs can only have potential energy. I guess if you throw a spring through the air, it's have got kinetic, I suppose, right? But so it's 250 times 0.4 squared, right? So I get 40. So I've got an object. It weighs 10 kilograms. It's moving at 5 meters per second. It has 125 joules of kinetic energy. Upon encountering the spring, it starts to compress it. When the spring is compressed 0.4 meters, the spring absorbs 40 joules of energy, meaning that how much kinetic is left over? Minus 40, right? Giving us a kinetic energy of 85 joules. And Jason, are we supposed to find the velocity?
Yeah.
Okay, so if it's got 85 joules, EK is equal to mv squared over 2. 10?
Yeah.
V squared over 2, and that's equal to 85. 85 is equal to 10 divided by 2 is 5v squared. So v is the square root of 85 divided by 5, 17. Yeah, that sounds about right. That's a really good example of sort of, I would say, pretty much the toughest question there would be, really.
Like, if you use 0.7 as like, 'cause that's the total distance, right? That it would go.
Yeah, 0.71. Yeah.
So if you use that,
Well, I didn't actually write it down here now.
oh, and like, could you put the 0.7 back in like the potential spring energy?
Yeah.
You could find your total energy using that.
Yeah, you'd be back to 125, right?
I got 122.5. Let me use that.
Well, there's probably a little bit of rounding going on.
But like, when do you know when you should be like adding dies or subtracting them or just using one or the other? Because you give us a bunch, and then sometimes you're like, oh, let's subtract another and use the difference, or hey, let's just use the new one to fix the difference.
Because what I did, and I subtracted.
Like you use so many different ways to do it to find the height, but I never know if I should be subtracting something from another to find the height or using another one given. Because you've done them both.
Can you show me examples?
Somewhere probably in here, but I can't now. You've given us like 5 booklets. So, find it.
Yeah, well, you look. I'll try to explain it. I need you to clarify the question. That's why I'm asking.
I remember there was one question that we did on like an example, it was like I think we threw something straight in the air.
Yeah,
And you know what I'm talking about?
maybe.
Yeah, landed on the leg.
Yeah.
I think that's what I'm talking about. I think we had to measure it at 0.4, and some people were doing 10 minus 6.
Oh,
It's like, but wouldn't you minus? Oh wait, no, 0.4 is your potential. So in this question, would it say like after it traveled the 0.4 meters, would that be now potential energy? And then
would what be potential energy?
well, so you'd put your 0.4 meters, and then you'd subtract that from your 0.7 meters, but you like put them all in the potential energy form. Like you find the potential energy from 0.7,
Yeah.
potential energy from 0.4,
Uh-huh.
and you subtract them.
I guess that would. Yeah, that would. Yeah.
And, okay.
Yeah.
I see what I did wrong. I
Yeah.
subtracted 0.3.
Yeah. Okay, so Hannah, let's try to go back to yours. Are you talking about something like this?
Well, there's those ones, and I found another one in your spring problem, question 13. Goes from one height to another, and.
Okay. Do you want me to do 13?
Well, I got 13, but I didn't know how. So, if you don't know to subtract one by another.
Well, how about I go through it then?
It makes no sense.
How about I go through it?
Yeah.
Okay. You read it out to me.
It's a long question.
Do you want me just to bring it up here? Or hand it to me?
Because it's the long one.
Okay. Okay. Yep. No, this is a good question to ask about. Okay, so we're looking at number 13 here on the questions with hook there in the corner, okay? Everybody kind of know where we are? Number 13, spring problems here. It says a spring has a constant of 400 newtons per meter. K is 400. An object is placed against the spring when it is partially compressed or partly compressed and then released so the spring pushes it away. So you're like pushing it against, letting it go, and it's going flying into the air. How much kinetic energy will the object gain as the spring goes from a compression of 80 to a compression of only 20? Hint, the EK gained by the mass is the potential lost by the spring. So, if you were just to lie the spring down, just let her sit on the table, let's just say that it would be 1 meter long. No compression, no stretching, it just sits. Okay? It has how much potential energy? Let me just go turn that off for you. It has 0. Right? Does everyone agree? Okay, so it's got 0. If I compress it, well, let's go a different color there. If I compress it 0.2 meters, does it have some potential energy now? It does, right? I've compressed a little bit. Okay, then I keep pushing the object up against it, and now this distance here is how far? It's 0.8 meters from its original amount. So I've compressed it 0.8 meters. It has a potential spring energy of, I'm going to put U80 just as a way of labeling it. It has 1/2 kx squared. That's an 80. So how much potential energy does it have? 1/2, 400.8 squared, which is, half of 400 is 200 times 0.8 squared, 128. I took this object, I pushed it up against the spring, it now has 128 joules of potential energy. How much work did I do, by the way, in getting it to that point? Yeah, I did 128 joules, right? I do 128 joules of energy, it goes into spring potential energy. Then I let it go. And the thing goes flying away, and at some point in that brief instant, the spring, as it expands, is at 0.2. So how much potential energy is left in the spring? 1/2 kx squared. Which is 200 times 0.2 squared, 8. The spring went from 128 joules of potential energy to only 8 joules of potential energy. So the EK, the change in EK is the change in potential, right? How much did my spring energy change? 120. 8 minus 128. I lost 120 joules, right? Therefore, my EK is going to be 120. Whatever spring energy I lost becomes kinetic energy gain, minus heat and friction. Sound. Does it ask how fast it's going? No, it doesn't. It's really, this question actually, Hannah, is no different than 14. It's just the opposite, right? Instead of the kinetic energy going into the spring, it's the spring energy going into the kinetic. It's the exact opposite. Give you all 100%. Yeah.
$20 bill.
What's that? And a $20 bill. Crisp one, too.
Well, that's what happened the other day when you guys were.
That's right, when those guys weren't here. I'm all out of 20s.
Oh, did you guys do the assignment? Or what did you do?
What was that?